So last class we discussed all these points. No? We finished binding energy in class. So the concept of radioactivity is not there. Last two concepts that are left out are reactions. You can make a note of it. So if you see those wrongly not able to give Nikhil and Ritika.
Uma, Harish.
So when you talk about the nuclear reactions, right? So like how you have these chemical reactions, we have so chemical reaction. What does we have? We have products. The products are combined. Sorry, when you have reactions, and the reactions are combined together, you're going to get different kinds of products. So what is involved there? What is involved in the process of the reactant getting converted to a product? There is some kind of a pollution taking place. You see on a molecular level, there is some amount of pollution that is taking place, which is making the product to get formed. If there is some change happening internally. In a similar way, when you talk about another type of reaction, which you call it as, so you talk about another type of reaction, which you call it as nuclear reactions, then here mainly the nucleus is going to get involved. you're talking about the nucleus getting involved, let's see how the reactions are going. But before that, they just gave some introduction. In 1990, what happened? Rutherford showed that by bombarding suitable particles, a suitable energy on a stable element, then element can be transformed into another element. What has happened? When you bombard a suitable particle on suitable energy on a stable element, you have a stable element, right? Then that element on which you are trying to bombard a third particle with can be converted into another element. And this kind of a transmission called as nuclear transmission or nuclear transmutation. The data is not available in text. It's called nuclear transmutation. So when we try to bombard alpha particles on nitrogen, right? We found that nitrogen was converted into oxygen. What is observed? Nitrogen was getting converted to oxygen. And this process can be written as the one which is shown below. This one. Nitrogen 14, when it is bombarded with alpha particles that is helium nucleus, then it gets converted to oxygen, but it is not getting converted to the stable element oxygen 16, rather it is getting converted to an isotope, right? Plus H11, a proton is getting released along with some energy that is free. And this kind of a process in which what has happened, a nitrogen nucleus has got converted to oxygen. So, in process in which the nucleus transmutation takes place are called as nuclear reactions. And generally, if you see Q is called as the Q value of the nuclear reaction, and it shows the energy produced in the process. So, based on this only, we will be defining the next two concepts, that is nuclear fission and fusion. Okay. And how do you generally write a nuclear reaction? This is the thing. Small a plus capital A will give you capital B plus small b plus q, or when you write capital A, inside the bracket, if you write the order plus small a comma small b, and you write capital B outside. What you're trying to say is when capital A is bombarded with a projectile small a, it gives you a product B along with a subatomic particle plus some energy. We call it as an emitted particle. Small. Or you call it as emitted particle, you call it as subatomic, generally call it as emitted particle. Capital B is the product nucleus. So it's given at the bottom. All the values are given. Capital A is called as the target nucleus, small b is called as the projectile, capital B is called as the product nucleus, and small b is called as the emitted particle. On the energy mass equivalence relation, we can see that the energy capital Q liberated in the process is equal to the energy equivalent. The increase in the mass of the process. If you want to calculate the Q value, it is calculated using this particular mathematical. Capital Q will be equal to mass of capital A plus mass of small a. This reactant appear, it will appear as the increase in the value of the kinetic energy. Speed of light. Speed of light. Square is there. Here, should I proceed? See, one unfortunate thing is I have to keep clearing the another make it. Should I proceed?
Yes.
Now, depending on what the value of Q, the value of capital Q is greater than zero, then it is called as exothermic or ERG, or one of the units of energy which can be used in less than zero reaction is called endo. Then evident that endo means the process which is absorbing energy cannot happen spontaneously. What is spontaneous? Light cell, solid state. Absorb some energy for it to undergo the reaction. Right? So, in nuclear reaction, it is necessary that the momentum, the electric charge, and the energy what conserved. Momentum, electric charge, and the energy each one is supposed to be conserved. So, if you want to see the conservation of charge, you can look at it by the numbers from atomic number, that's the mass number and the or mainly see when you talk about charge, you don't take the mass into consideration because nucleons from nucleons only protons are going to contribute. So moreover, the sum of the atomic mass numbers before and after reaction are equal, but the mass can change. In short, we will know the Q value of the reaction is equal to energy equivalent to increase in mass of the reaction, which is also equal to the increase in time. Next stage, numerically, if you add the mass number, it will come out to be the same. But if you try to take those particles and put it on a spectrometer and try to measure the mass spectrometer, you will see that there is a slight change. There will be a decrease in the value. The decrease in the value is going to appear in the form of increase in kinetic energy. As I told you, this is not there at X4. And this is the basic for you to understand the concept of. So you see, right, when Rutherford's experiment was done, what was discovered? Yes, they didn't know that nucleus. But at that point of time, people started believing that nucleus is completely positively charged, which is a fact. So when it is a positively charged thing, what do you think? It has only protons. What is not possible? The neutron numbers. So later in the year 1932, James Chadwick, he was discovered. Therefore, Fermi suggested that as neutron is electrically neutral, it does not have to face the Coulombic repulsive forces, and hence by bombarding neutron in the nucleus, you can go deep into the nucleus. Neutron itself can be treated as a very good projectile. Because neutron does so when you think of the alpha ray experiment, this was the nucleus, alpha particles had positive charge. The positive charges underwent deviation or they returned back only because of the Coulombic repulsion that was happening. That is why we had a concept called as distance of closure approach. So if I use an alpha particle as a projectile, I'm going to experience this. But logically speaking, after the discovery of neutron, one big advantage is you can treat neutron itself as a projectile. If it is going to the nucleus, increase the number of neutrons, there is something called as neutrons to proton ratio. If that value is increased, the nucleus will become unstable. It is then reaction is stable. Unfortunately, what has happened, radioactivity is not there. Nuclear fission is actually artificial radioactivity. You know what is radioactivity? Radioactivity, see, generally there are two types of reactors. So in chemical reaction, if you see, shells are going to participate. There is going to be a repulsion or attraction taking place with electrons. Whereas in nuclear reaction, the nucleus is the name is the nucleus itself is going to get involved. So if I have to talk about a natural nuclear reaction, it is radioactive. As long as something is stable in this world, it can be a nucleus or an atom or something. So here our concentration is on nucleus. As long as the nucleus is stable, even somebody is disturbed, they are going to disintegrate. In a similar way, if you are going to disturb the equilibrium of the nucleus, it will start reacting. Right? So, depending on the binding energy curve that we discussed last class, you remember? I showed you a graph. There are certain heavier nuclei which are naturally unstable. If you try to find them, they will start reacting. Let's say they are under they're deep inside the earth. You dig it and take it out, you start reacting. So you need to handle it with care. So if it starts reacting naturally, then you ask me how is it going to react? So the nucleus which is unstable will try to disintegrate itself by itself, it is spontaneous, by itself into smaller nuclei of stable values. That's what is called as radioactivity. Why is radioactivity happening? Because it has so much of energy that it wants to release. So these nuclear reactions are something like radioactivity. Basically, nuclear fissions get radioactivity only, but it is a man-made radioactivity. Meaning, you will have a stable nucleus which has nothing to do, but you will use a projectile and disturb the equilibrium and make it undergo radioactivity. So when this radioactivity is undergone, there will be liberation of particles like alpha particles, beta particles, and gamma. Then you need to understand the basics of nuclear transmutation. The basic structure of nuclear reaction, capital A, you have a target nucleus. It is bombarded with why is it using that? Only to create instability in the target nucleus. That is why they told neutron itself can act as a good projectile because the whole of nuclear fission runs with neutron. Like you see, when Hahn and Stutzman bombarded thermal neutron of energy, which is 0.04 electron volt, on compounds of uranium, they found that barium is the newly formed radioactive element. What happened is the uranium nucleus was bombarded with neutrons. Then it started getting unstable in the first place. Then it got disintegrated, out of which one of the products that was released was barium 144 and 56. Along with it, you will see another product krypton to become stored. Okay. They were surprised with the result. Then, see, there were many scientists who carried out this process. You need not remember the names. Okay. There are two other scientists who found that when thermal neutron is bombarded on uranium nucleus, It disintegrates uranium nucleus into two almost equal parts, and in this process, what happens is you can observe that there is enormous amount of energy that is getting released, and this reaction is called as nuclear fission. Fission basically means disintegration of a bigger nucleus into smaller stable nuclei of almost equal masses. Okay. So, in the fission of uranium, many different nuclei have been obtained. Okay. This is how the reaction happens. Now connect all the dots. You have uranium 235, on which you use the projectile neutron. So it became uranium 236. So basically uranium 235 is a stable nucleus, but its isotope uranium 236 is unstable. Now this starts getting disintegrated into two other nuclei. One is barium and the other is krypton. Along with this, what is happening is there are three more neutrons that are getting released along with energy. This is where the dangerous spot is. What will happen is this free neutron, see, one neutron itself could release enormous amount of energy. These free neutrons will again undergo a reaction with uranium-235, making it 3 times unstable. So you will have 3 unstable uranium-236, which will release 3x energy, which will become uncontrollable because those 3 neutrons will release 9 more neutrons, and 9 will release 27. It keeps on going. This is what is called as a chain reaction. So we wrote it here, we wrote things here, that's a different story. But in reality, you cannot handle it like this. Okay. So again, the same uranium-236 bombarded with neutron, you have uranium-236. You have neodymium or something we call it. There's 4 more neutrons, plus energy is getting released. Similarly, uranium-235 plus neutron is going to give you xenon and strontium. So plus 2 neutrons and some energy, right? And the most important point is the product nuclei obtained by fission are called fission fragments. It is like a bigger nuclei getting disintegrated to smaller. I'm not sure if in your 11th standard you remember this. There is a nuclei or a shell which has got disintegrated into two other lighter nuclei. You will apply the concept of conservation of failure momentum to solve. Connect the dots. They told you in the beginning, nuclear reaction, what is supposed to be conserved? That is why you say the momentum is supposed to be conserved, because all these things are happening because of the internal energy or internal forces, nothing to do with it. Okay. So neutrons are called fission neutrons, and the energy is called as the fission energy. So if you observe in the above reaction, 60 different nuclei are obtained as fission fragments having the atomic number ranging between 36 to 50. Reactions like this, they observe different kinds of nuclei that got released. Okay, the probability is maximum for the formation of nuclei with mass number 95 and mass number 140. And the fission fragments are radioactive, and by successive emission of 13 particles will result in stable nucleus. So radioactivity means spontaneously, if an unstable nucleus is getting converted to stable nucleus with the release of energy. Unstable will get converted. Unstable one will get disintegrated. Radioactivity. Radioactivity, you have no neutron, no projectile, anything. Everything will happen on its own. Okay. So whenever there is an unstable nuclei that is getting generated, there will be 13 particles are getting released to form that stable nuclei. And the neutrons produced in this reaction are fast. You saw the number of neutrons, no? They are very fast and they have the energy of 2 megaelectrons. Okay. And similarly, if you see the Q value of this reaction, that is energy produced, this very large rate, somewhere around 200 megaelectron volt per fission. Radioactivity, I will not call it as a chain reaction. Not maybe it takes multiple steps. You cannot Let it stop. See, this word anything that is stable will not react. Anything that is stable will not react on its own unless you go and discuss it. So this energy is obtained due to what? Due to the mass difference between the reactants and the product. We discussed the beginning. Now Q is equal to MA plus small m small a minus MB minus m small b c square. So that is the value they are trying to say. Initially, this energy will be in the form of kinetic energy of the fission fragments and the neutrons, which eventually transfers into heat energy in the surrounding material. So in a nuclear reactor, now if the question starts, where does all this reaction get carried? It gets carried in a nuclear reactor. So in a nuclear reactor, which produces the electric power through successive nuclear fission process take place, but in a controlled form. So what happens inside a nuclear reactor is nuclear reactor mainly runs the process of nuclear fission, but control the process by doing certain absorption. Those three neutrons are released, we do not allow the multiplication factor to happen. So there are certain elements which are used inside, which have a specific functionality. That's what we are going to discuss. So generally, if you see a nuclear bomb, what happens? Nuclear bomb undergoes fission, but it is an uncontrolled fission. So there are two types of bombs: nuclear bomb and atom bomb. Atom bomb is an application of nuclear fusion. The nuclear bomb is an application of fusion. With Russia, they written also of a nuclear bomb. Uncontrolled. So the theoretical explanation of nuclear fission is given by liquid drop model of the nucleus, in which nucleus is compared with the drop of a liquid. Okay. Now we are going to get into the context of nuclear chain reaction and a nuclear reactor. Shall I proceed? Those who are online are able to understand?
Yes, sir.
Oh. So nuclear chain reaction and nuclear reactor. Right. So we saw the reaction. In the previous article, we have seen that in fission process uranium-235, by using a slow neutron. So if you use a fast neutron, what it happens? It appears and goes, it will not participate in the reaction. The nucleus itself is very small. What happens? Uranium-235, what did you actually do? Uranium-235 meaning another. Mass number is 235, means the number of nucleons are 235. So when the nucleons are 235, it was stable. When this newly formed, when this projectile neutron is going and sitting inside the nucleus, what happens to the mass number? It went to 230. It is then retarding unstable. So for you to carry out a reaction, you need a slow neutron, not a fast neutron. Fast neutron, what will happen? It will go and will come out. In the previous article, we have seen that in fission process of uranium-235-92 by a slow neutron, one or more neutrons are emitted. For every fission, average of 2.5 neutrons are obtained per fission. To take the average, it is somewhere around 2.5. Reason for the fraction which appears here is that certain fission processes we get 4 or 3 or 2 neutrons emitted. You saw that, right? Some emitted 3, some 2, some 4. If you take the average, it comes to 2.5. So in 1939, Fermi suggested that with the help of neutrons produced in this way, if fission of other uranium nuclei is accomplished, then you will get still more energy and still more neutrons. A series of such processes is called as nuclear chain reaction. So what it is suggest? With the help of neutrons produced, if you carry out the reaction again, instead of taking some other neutron, you can create a chain reaction. But how should the chain reaction be carried out? In a controlled way, not in an uncontrolled way. Okay? If such process is properly controlled, then the energy can be obtained continuously at a steady rate. Then you will get more energy, but we will not be there to consume. Okay? So So nuclear reactor is the illustration of this. Means that is the mission I can say which is used to carry out this kind of a process. Right? If such process occurs in uncontrolled manner, then the energy produced cause explosion nuclear bomb is the illustration of this. So what does a nuclear reactor do next? It carries out the nuclear chain reaction in the uncontrolled manner. So now we shall see the difficulties encountered in the success of such nuclear chain reaction in the removal. So what are fission neutrons? The neutron is generated in the fission process. Are generally fast. They have an average value energy of 2 megaelectron. First thing what to do, they should be stopped from escaping the fission material. Fission material is the target nucleus. Right. Moreover, they should be slowed down and converted into a thermal neutron. Means its energy has to be brought from where 2 megaelectron 0.04 megaelectron. Okay, to become suitable for this fission reaction. So to stop neutrons from escaping, neutron reflecting surfaces are used, and the neutron reflecting surfaces are used, and the arrangement of fission material, the surface for volume ratio is kept low because the nucleus process of neutrons is a surface process. The surface processing happens from the surface. So what are they going to do? They will have some reflecting surfaces so that the neutron goes hits and gets reflected. Now comes the question. They'll ask you an example. To slow down the neutrons, what do you use a material called as the moderator? Right? Generally, you see moderator, normal water or heavy water, graphite or beryllium are used. So what do they generally do? They actually slow down the neutrons but do not observe. Means the neutrons will not get mixed up with water or heavy water, rather they get slowed down. Slow down the water. In producing fission of uranium-235, slow neutrons are as more effective as compared to fast neutrons. Okay. In such a chain reaction, enormous heat energy is produced and the temperature is likely to become 10 power 6 Kelvin. Sufficient moderator, etc. should be cooled and that heat energy should be converted into some. When the chain reaction is happening, there is going to be a lot of heat energy that gets used and of 10 power 6 Kelvin means almost 1 million Kelvin for 10 times. Okay. So moderator only does what? If you slow down the neutrons, but who is going to control this? It's heat. What you need is. So water, molten sodium metals, gases, etc. are passed as coolants through the tubes in the fission chamber. Are you understand this? So if you look at the nuclear reactor, it's going to look like this. You have something called as control rod. You have a core, hot water circulated, water cooled, cold water circulated. You have a pump. Steam at high pressure, you have a turbine, and the turbine is what is going to be connected. Right? Then you have steam at low pressure, cold water, hot water, everything. So there are certain points to be noted. In nuclear chain reaction, the ratio of the number of neutrons produced at any stage to the number of neutrons incident at the stage is called as the multiplication factor. So what is the ratio of the number of neutrons produced? So in one of the reactions, the number of neutrons produced is 3, divided by the number of neutrons which participated initially in the reaction. 1. So the multiplication factor means neutrons are more 3 times. When K is equal to 1, the reactor is said to be critical. If K becomes greater than 1, the nuclear reactor is said to be supercritical, right? In this state, the rate of reaction and the energy abruptly increase and explosion takes place. So for you to avoid all these things, what could happen? K should be maintained at less than 1 subcritical state. This process slow down and eventually stops, and we cannot get energy continuously. K should not be less than 1 also. So if K becomes less than 1, what will happen? It will come to the subcritical state and the process slow down. And at one point, what will happen is the whole process will stop and we will not be getting energy continuously. In order to control the value of K, rods of materials which can absorb neutrons come up, like cadmium and boron. And these rods are controlled automatically. So if the value of K tends to be more than 1, the rods go deeper in cushion material to absorb more neutrons. The value of K tends to be less than 1, these rods automatically resorted to decrease absorption of neutrons, and these rods are called as. So thermonuclear fusion in sun and others. So we are done with nuclear fusion. And we are going into nuclear fusion. Fusion, as the name suggests, is a combination of molecules. Right. So the sun has been emitting energy at a tremendous rate of 3.8 into 10 to the 26 joules per second. Amount of energy it keeps liberating every second. And how many years will it be doing? Okay. The origin of such enormous energy remains unknown to scientists for many years. What happened? But what happened? Fortunately, nuclear physics could explain why this is happening. So, nuclear physics gave an explanation to this, and energy is obtained by the fission of. Okay. Listen. Fission is what you need a heavier nucleus which is getting split into smaller nucleus, but there is a counter operation to this also. When two proper light nuclei are fused together at a very high temperature to form a thin nucleus, even then what will happen is there is an enormous amount of energy that will be, and such process is called as thermonuclear fusion. Thermo refers to temperature, nuclear is nuclear. Fusion is formation. For example, when you take the helium nucleus, the helium nucleus is made from protons and neutrons, then much energy is going to get produced. Here, in the sun and other stars, the energy is produced by thermonuclear fusion. Okay. Now we are going to read about different kinds of cycles. your sense.
application
In sun and other stars, what is going to happen? Energy is produced by the thermonuclear fusion. So these are the different kinds of cycles. So in sun, energy is produced by a process called as proton-proton cycle. So which occurs according to the following stages. Why is it called as proton-proton? H11 is a proton, other H1 is also proton. They both get combined to get a neutron plus an element is getting released. Any idea about what is this? It's called a positron. Called positron plus an anti-neutrino plus some energy. Right. Now what will happen is this positron will get combined with an electron to give 2 gamma. Gamma is not a particle, it is energy. Plus 1.02 mega electron. Now what will happen is this H21 will get combined with another proton, will give you helium-3 nucleus plus gamma radiation plus 5.49 mega electron. And lastly, the helium-3 and the helium-3 will get combined with each other to give you helium-4 plus a proton and a proton plus 12.86 mega electron volt of energy. So when first 3 reactions occur twice, 2 helium-3 nuclei are produced and the fourth reaction takes place. As a result of all 4 reactions, 4 protons, 2 electrons produce 1 alpha particle, 2 neutrino, 6 gamma photons, and here if you calculate the energy, 2 into 0.42 plus 2 into 1, so 100. 2 into 0.42 plus 2 into 1.0 plus 2 into 5.49 plus 12.86 will give you a total of how much value? They've told here, listen to this. So calculate. So read the statement. when first three reactions occur twice, right? When the first three reactions occur twice, what will happen? Two helium-3 nuclei are produced, and between them, the fourth reaction takes place. Capturing the previous one, and between them, the fourth reaction takes place as a result of all reactions. If you take all the reactions, how many particles are actually participating? Four protons. So what did they say? All the first three reactions will occur twice. Four, so 2 into 2 plus 2 electrons plus 1 alpha particle, right? Plus 2 distinct neutrino plus 6 times gamma. So 2 plus 1 into 2. So 6 times gamma photons. Here, the energy equal to how much value? 26.7 megajoule is liberated. Moreover, there is another process called as carbon-nitrogen cycle, okay, which is also suggested for the energy produced in the stars. We shall not go into details, so it is not needed for us. We only discuss mostly about this proton-proton cycle. Okay. So it will take further how many years? 500 crore years for all of the hydrogen in the core of the sun to burn out and become helium. Thereafter, since combustion of hydrogen stops, sun will start cooling down and it will collapse due to its own gravitation. This is what they say. Based on the calculation, the prediction is after 500 crore years, sun will cool down and collapse. I'm not worried about it. If these things are not needed actually, it's like a story only. Exam point of view is not there. But share this with basic reason. Where this reaction is carried out. Otherwise, we'll see what are the hazards, what are the dangerous aspects of this. So the energy produced by nuclear fission and nuclear fusion is found to be useful in many ways. Right? But at the same time, there are certain laws in terms of human beings also that can occur if there is a small signal. Right. So the destructive effects of atom bomb have already been experienced in nuclear. Although getting power from nuclear reactor is beneficial, the waste products from it are intensively radioactive and hence are harmful to the living bodies. Might not be to us, but the ones which are released into water bodies or something might affect organisms. No satisfactory solution is still found to store them or to dispose them. So the main problem is this is maintenance. Moreover, accidents occurring in such reactors can cause destruction in the surrounding environment. But yeah, people who are working there are supposed to get more option. But as far as possible, you need to stay away from it. Okay. But these things again are not examples. So we have to talk about the examples I already gave you. That you need to read from your textbook. There are some more reactions given with respect to part of take the notes, write down the any other doubt? Yeah. Wind up. Those are online.
Yes, sir.
Where's the cables?
Yes. Yeah, we'll wind up.
Yeah, thank you, sir.
The sounding